Hi, I'm Norman Wildberger. Today we're going to be looking at the trigonometric laws in hyperbolic geometry using Geometer's Sketchpad. This is the 26th lecture in this course in Universal Hyperbolic Geometry, and we've entered the second part of the course where we're mostly interested in metrical notions and the laws of trigonometry. Now, in Universal Hyperbolic Geometry, which is a wider and more accurate and arguably more beautiful theory of hyperbolic geometry, the main metrical notions are not distance and angle as they are in classical hyperbolic geometry, but they are rather quadrants and spread. These are purely algebraic notions that can be computed accurately and precisely in many situations. And those are the concepts that we're going to be talking about today. So our setup is that we have our basic null circle right there in blue as always, and we have a distinguished triangle here created from the points A1, A2, and A3. And we're allowed to drag them around. They don't have to stay inside the circle, and it's very important that all the laws that we're going to be talking about apply whether or not the points are inside or outside the circle. Now, of course, the 3 points determine also 3 lines, the 3 lines of the triangle. So today we're going to be looking at the 3 quadrances formed by this triangle and the 3 spreads formed by this triangle and the various trigonometric laws, which are over here: Pythagoras, triple quad formula, the spread law, and the cross law. So let's start by talking a little bit about the quadrants between 2 points. This is a custom tool that I've created. It's over here, a little bit below your view. I'll get the quadrants tool, and now we can measure quadrants by clicking on any 2 points. Let's click on A1 and A2, and we see that the quadrants comes up, and it happens to be minus 11.51. If we move A1 and A2 around, this quadrant is changing. If we move A3 around, well, the quadrants doesn't change as we would expect. The quadrants is negative if the 2 points are inside the circle, but if one of them moves outside, then the quadrants becomes positive. Well, not always positive. Here it's negative. Here it's positive again. Okay, so let's now find all 3 quadrances, and I've already done that, so we can get rid of this one, or rather first I'll show you the 3 quadrances. There they are right there. So the one that we've just found is encoded here. This is to 4 decimal places. That's Q3 because it's the quadrants between A1 and A2. We also have Q1, which is the quadrants between A2 and A3, and the quadrants Q2, the quadrants between A1 and A3. So let's delete this and just have a look at these 3 quadrances here as we move the triangle around. Notice the quadrants Q1 here between A2 and A3 is pretty well close to 0 because they're almost on this null line. Alright, so those are the 3 quadrances. What about the 3 spreads of the triangle? Well, let's look at, for example, the spread formed by these 2 lines. The notion of spread is completely dual to the notion of quadrants. So the spread between these 2 lines is exactly the same as the quadrants between the duals of those 2 lines. The duals of those 2 lines can be found by the pole tool. If I click on A1 and A3, I get this point here, which is the dual of this line. If I click A1 and A2, I get this point here, which is the dual of this line. And now if I go to the quadrants tool again and find the quadrants between this point and this point, this is now the quadrants between this point and this point, we see that it's the same. Where was the spreads? It's the same as the spread S1 between the two lines that meet at A1. So we can delete this, and I can hide these for now. And now let's have a look at the three quadrants and the three spreads as we move the various points of the triangle around. If the 3 points are inside, then the three spreads are all between 0 and 1. They correspond kind of roughly to the spreads in rational trigonometry. One of the points are outside or more, then the spreads can also become negative. Alright, so trigonometry is concerned with the relationship between these 6 numbers. And there are 4 main laws: Pythagoras' theorem, the triple quad formula, the spread law, and the cross law. Now let's illustrate these various theorems. The first one, Pythagoras' theorem, is illustrated for a right triangle. And to get a right triangle, let's talk first about the dual triangle of the original. This new triangle that I'm just showing you here now is the dual triangle of A1, A2, A3. And how did we get that? Well, the points of the triangle, say this one here, are the duals of the lines of the original. So the dual of this line here is this point. The dual of this line here is this point. And the dual of this line here is this point. So this triangle here is the dual of the original triangle. Conversely, the lines of the dual triangle are the duals of the points of the original triangle. This is the dual of that, and this is the dual of that. And you can see how the dual changes as we move our points around. Needs to go off the page, of course. Alright, so now let's have a look at when our original triangle might have a right angle at this point here. In other words, when these two sides are perpendicular. When will that happen? That will happen when one of these lines goes to the dual of the other line. So the dual of this line here, A2, A3, is this point here. So if we arrange by moving A1 that the other line here passes through this point, then these two lines at A3 of the original triangle are perpendicular. And note that that happens precisely when this line here is passing through this point here, which is the dual of this line. So both of those facts are telling us that these two lines are in fact perpendicular. And so Pythagoras' theorem should hold. Let's have a look at what Pythagoras' theorem is about. So Pythagoras' theorem is the relation between the quadrants Q3, which in this case is the opposite quadrants here, Q3, and this quantity Q1 plus Q2 minus Q1 times Q2. Q1 is the quadrants here, Q2 is the quadrants here, and here is this combination Q1 plus Q2 minus Q1 times Q2 equals minus 3.8970. Now, if our point was situated so that this line was going exactly through here, then we could expect these two to be exactly the same. Now one way of making that happen is to force that to happen. So suppose we make a line between this point and this point. Let's give it some different color so it looks a little bit different. Say blue. Now if we want to, we can put this point on this line, and that should give Pythagoras' theorem. But we can actually force the program to do that for us automatically by telling it to merge this point with this line. And we do that by going up here to the Edit tab and going down to Merge Point to Line. And you will see that the program has automatically moved A1 onto that line that we created between this dual point and A3. And we can move A1 now, but it's constrained to lie on this line. And now you can see that in fact Pythagoras' theorem holds exactly. To 4 decimal places, Q3, this quadrant's here, really is Q1, this quadrant's, plus Q2, this quadrant's, minus the product Q1, Q2. So we're seeing Pythagoras' theorem working here. We can even go on the other side, it doesn't matter. Anywhere we go, these two numbers are the same. And we can move this point as well, because that's not going to change the perpendicularity. Okay, so now let's edit again, and we're going to split the point from the line, and we can get rid of this line. We don't need it anymore, and we've illustrated Pythagoras' theorem, so we'll close that. I'm going to get rid of the dual triangle. And now let's look at the second main law, the triple quad formula. The triple quad formula is telling us what happens when 3 points are collinear. And here it is right here. So what is this? This is a computation that is formed with these numbers. Now how does one actually make such a computation? Well, under here in the tab bar, under number, there's a calculate sign. So suppose we press that, and now we can input anything we want, but we can also input quantities that we've already calculated. So for example, suppose I wanted to calculate Q1, and then I'd say plus Q2. Okay, so then this would calculate for me Q1 plus Q2. And that's what's happening here, except it's a little bit more complicated. I'm calculating Q1 plus Q2 plus Q3 squared minus 2 times Q1 squared plus Q2 squared plus Q3 squared minus 4 times Q1, Q2, Q3. This is the S function, the triple spread function that we defined 1 or 2 videos ago. And here we see that it has the value 57.68. We don't need this, let's get rid of it. And now let's have a look to see when the triple quad formula is going to work. It's supposed to be 0. This quantity is supposed to be 0 if the 3 points are collinear. So let's see if that happens. If we move the points closer to being collinear, then the 3 quadrants here are not 0. We're still talking about quadrants from here to here, quadrants from here to here, and quadrants from here to here. But these 3 numbers satisfy a relation. And this is the relation that they satisfy. This thing squared minus 2 times this minus 4 times that is 0. And we can make that more accurate by doing the same kind of thing we did before by merging the point to the line. Now this point is actually exactly on the line, not just approximately the way I moved it by hand. It's forced to stay on the line. And you can see that as we move it, the 3 quadrants are changing, but this expression is constantly 0. This is showing us the triple quad formula. And we can see furthermore that it doesn't matter where these 3 collinear points are. They can be everywhere. This formula is constantly calculating this quantity, and it's always getting the value 0. Alright, let's undo that. Let's split the point from the line. So now it's triangle again, and we can get rid of the triple quad formula. Okay, there are two other important laws. The spread law is the next one. What does it say? It says that if you calculate S1 divided by Q1, if you calculate S2 divided by Q2, if you calculate S3 divided by Q3, here are those calculations, then you always get the same ratio. So S1 over Q1 equals S2 over Q2 equals S3 over Q3. And you can see that, in fact, those three things are always the same. And it's not just when the points are inside. The points can be anywhere they want to be. The spread law is always holding. And finally, the most complicated law is the cross law. So let's have a look at that. So what does this say? Well, here's the cross law. Actually, one of three cross laws, because there's one sort of for every vertex. So this one says that if we look at Q1 times Q2 times S3, so the spread here at this vertex here, and then we subtract Q1 minus Q2 minus Q3 and add 2 and square it, then we get 4 times 1 minus Q1 times 1 minus Q2 times 1 minus Q3. And I'm illustrating the law by calculating the difference between the left-hand side and right-hand side, and we're seeing that it's always 0. And you can check that that's actually true. Here I've done the two sides individually. Okay, so there is the standard left-hand side of the cross law. There's the standard right-hand side, calculated to 4 decimal places, 1806.5522. And you can see what happens as we move the points around. These two numbers are always the same, so of course their difference is 0. In other words, this quantity always equals this quantity for any triangle. And this is just one of three possible laws. We could replace this first term, Q1, Q2 times S3, we could replace that with Q1 times Q3 times S2, or with Q2 times Q3 times S1. All of those three quantities would be the same, in fact, and they would all satisfy this left-hand side equals that right-hand side. So we'll have a little look. No matter where we are, this beautiful law is always satisfied. So I hope you're getting some appreciation for these formulas. They may look complicated, they may look like they're quite involved, but in fact they're enormously simpler than the corresponding formulas in classical hyperbolic geometry. The corresponding formula in classical hyperbolic geometry is called the Cauchy law, and there's in fact usually two of them. There's also a dual law to all of these four laws, but it turns out that the dual law has exactly the same form because of the duality between quadrants and spread. While in classical hyperbolic geometry, the dual Cauchy law is subtly different from the original Cauchy law. In any case, these laws here that I'm showing you here only rely on high school arithmetic. It's basic algebra using pluses, minus, times. Those are the operations that we need, and it's easy to check any of these laws in any particular situation very explicitly with pen and paper. So these are very important laws, and our next job is to start thinking about how do we prove the spread law and the cross law. Well, both of them are going to involve some work. So in our next lecture, we're going to start looking at the spread law. Very important law, and we're going to have a good look at it. I hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.